Pode começar.
Good morning. I will start we will have now, I'd like to invite Kalinka Castelo Branco, the director of our institute, ICMC, to say a few words. Thank you, Kalinka.
Good morning, everyone. It's a pleasure to open this meeting. So it's a great joy to welcome you all to São Carlos for the 19th International Workshop on Real and Complex Singularities. To those returning, welcome back. To those here for first time, we hope ICMC feels like home by the end of this week. Since 1999, this workshop has brought together research from around the world, growing in one of the most cherished traditions of the Singularities community. And this tradition has a heart and a name. Professor Maria Aparecida Ruas, our beloved Cidinha. This is our first workshop without her, and her absence is deeply felt. Cidinha was not only a founder of this meeting and a brilliant mathematician, she was a generous mentor, a builder of bridges between people and ideas, and a friend to so many of this room. The warmth you will feel this week in the talks, in the coffee breaks, in the collaboration that begins here is her legacy. We dedicate this edition to her memory. May this week be filled with beautiful mathematics, new friendships, and the spirit of generosity that Cidinha taught us all. Welcome, and thank you for being here. I had to write because it's difficult to say this word without her here for the first time. Thank you all. Make this a beautiful event to honor her. Thank you, Miriam. Thank you, Thais. Thank you all of us to being here at ICMC.
Thank you very much, Kalinka. In the name of the organizing committee, especially our coordinator, Thais Dalbello, I'd like to welcome all of you to the 19th International Workshop on Real and Complex Singularities. So this workshop is dedicated to Maria Aparecida Ruas, our dear Cidinha. Honoring her has been one of the main motivations behind the organization of this edition. This workshop brings us mixed emotions. It's marked by the sadness of losing her, whose absence is deeply felt by all of us. At the same time, it's filled with gratitude and joy as we continue to build upon everything she gave us, her mathematical vision, her generosity, her enthusiasm, and the community she helped create. In moving forward together, we celebrate not only her remarkable legacy, but also the lasting inspiration she continues to provide to all of us. The presence of each one of you here today plays a very meaningful role in this tribute. Together, we represent the scientific community to which Cidinha devoted much of her life, and which she helped shape in such a profound way. I believe that much of her life in which she helped the gathering reflects one of the most beautiful aspects of scientific research: the communities, friendships, and collaborations that endure across generations. On behalf of the organizing committee, it's our pleasure to welcome all of you. We are very happy to see researchers, students, collaborators, and friends coming from many different institutions and countries to join us for this week of mathematics and scientific exchange. One of the things that makes this workshop so special is its tradition. Over the years, it has become much more than a meeting on singularities and applications. It's a place where ideas are shared, collaborations begin, old friendships are renewed, and new ones are formed. I would also like to thank those who worked to make this event possible. So first, our sincere thanks to the workshop members of the organizing committee for their dedication and commitment. We thank the members of the scientific committee for their dedication and valuable work in selecting a high quality works with a program, a high level program of contributions. I would also like to acknowledge the support of the events team and operational support staff. Let us also present the group of students, so please, very quickly, if you are around, please come here so everybody can see you. During all the week, they will be ready to help speakers, session chairs, and all participants with directions. So here they are, using these very special t-shirts. We gratefully acknowledge the support of our funding agencies, I have to say that, and institutional partners. So it's a great team. Thank you very much. So let me acknowledge the CAPES, CNPq, FAPESP, UFSCar, Pró-Reitoria de Cultura e Extensão of the University of São Paulo, and this institute, ICMC. Their support has been essential for the realization of this workshop. Let me say quickly a few words about the program. We have an exciting week ahead of us with plenary talks, parallel sessions, and poster sections covering a wide range of topics related to real and complex singularities, and there are many connections with other areas of mathematics. The schedule with possible updates will be available throughout the workshop on the conference website and will also be displayed, okay, on the information board in the main hall. So keep an eye on that, please. Another thing I want to say, please keep your badge visible at all times while attending conference sessions, coffee breaks, and the barbecue as well. Thank you. Today at 5:30 p.m., we will gather here in the auditorium for a tribute video dedicated to Cidinha. I hope all of you will be able to join us in this very special moment. I'd like to point out that there is a printed schedule by the reception desk of session chairs assigned to each lecturer. So that's what you are going to see outside there. We kindly ask all session chairs to check it and note the times of their sessions. Finally, we thank all of you for being here. The success of the workshop is not measured only by the quality of these talks, but also by the people who participate in it. Your presence, your ideas, your questions, and your interactions are what make this event truly meaningful. I wish all of you an inspiring week full of stimulating mathematics, fruitful discussions, new collaborations, and enjoyable moments with friends and colleagues. Thank you.
Hello. Hello, everybody. It's a great honor for me to be the chairman of this first talks of the week. It's quite hard for me to be here because I was not just a student, supervised by her, by Cidinha, a friend. She was like my second mother. But we have to keep going on. So I have the pleasure to announce the first talk of this morning is given by Isabel Laboriu, a great friend of Cidinha already, and she will give a talk on counting with Cidinha. Okay, please, Isabel.
Água aqui. E a minha. Ok, sim. Tem alguma coisa para clipar? Pode ser isso aqui. Vai.
Luiz, depois você desliga o microfone da tribuna, por gentileza, Luiz.
Okay, all technical part done. So, first of all, thank the organizers for organizing this fantastic meeting. I'm sure it's a lot of work that they had to do to organize it, and it's going to be a great success, like all the 18 previous meetings. And since this is a conference in honor of Cidinha, I want to say a few words that I wrote because I'm scared of emotion. I'd like to say a few words about her. So, I first met Cidinha at this Warwick one-year symposium on singularity theory at Warwick. We both attended the symposium, and we were also neighbors in these little houses, which were the mathematics research houses. So that's when we became friends. And after that, the next year, Cidinha invited me to São Carlos for a 1-month visit, which was great. And during that month, I made many friends here in São Carlos. And especially I met Miriam Manuel, who just talked to us, who was at the time an MSc student of Cidinha. At that time, I explained to Cidinha why I was not very happy with what I was doing in research at the moment. This ended up being the beginning of our first joint paper. It was on nerve impulse equations, imagine. Cidinha working on nerve impulse. This was the first of many visits, of many of my visits to São Carlos, to the institute here, and also of a few visits of Cidinha to Portugal, in which we worked, we had developed further our friendship. And as you see, Gaspar is not in the picture because he was behind the camera. I love this beautiful picture with the Douro River in the background. Okay. I have learned a lot from Cidinha. I learned lots of mathematics, and I also learned how to be a conscientious mathematician, how to be a mathematician that pays attention to what's around her. During those visits, several visits both ways, we produced another joint paper, which is this one in Singularities, and we started on another one, but we were both very busy with other things at the same time, so we never finished the paper. And this is what I'm going to talk about, our unfinished paper. You're going to see it's quite unfinished. So the real title of the talk should be this: Counting AN points of the real stabilizations of covariant 1 singularities, joint work of Cidinha and me. So what is it about? Let's see. Now we start doing mathematics, it's easier. So the setup is you start with a smooth map germ, a very simple thing, finitely determined, covariant 1 under left-right equivalence. Okay. And this means that in general, you can rewrite it in the form of all it's covariant 1, so all the x variables, n minus 1 x variables repeated, and a function open. I always do this. Always a g of xy, so it's a map from Rn plus Rn into R, right? And we look at the stabilization of this little f, which is a map germ, capital F, of the same form as the little f, except that now it depends on a variable t, an unfolding variable, one-dimensional. And we are assuming that the only singularities of this map F, capital F, for fixed t are of type AJ with j less than or equal to n. And the aim is to obtain the number of AN, count the number of AN singularities in the given, oops, I always do this. I get it wrong. Obtain the number of AN singularities in a stabilization, in a given stabilization, capital F of little f. Okay, so let's go. There's an easy part of this, which is an upper bound. It's a well-known result that if you take the ideal generated by the conditions that give you an AN singularity, that is the derivatives of little g with respect to y up to order n, you take the ideal generated by that over the set of functions in xy. If you quotient this ring over this ideal, its codimension gives the maximum number of singularities. Actually, it gives the number of complex solutions to the equations, these derivatives of g equals 0, right? So that's an upper bound for the number of real solutions. The problem is this number is the same for the number of solutions for a stabilization, in a complexification, in the complex context, is constant over all, let's see, I think it's here. It's constant over all possible stabilizations, but for real stabilizations, it's not constant, right? It depends on the stabilization you choose. So I'm going to have this notation that sigma of f is the codimension of this ideal, which is then counts the simple solutions, complex ones, and the effective number of real solutions I'll call S, and it's going to be S plus the number of real solutions for positive t and S minus for negative t. Since there's a lot of notation, what I did was I wrote the notation in the blackboard. So you can keep the notation there and I don't have to keep repeating it. At least I do have problems in keeping track of notation along a talk. Okay, so as I said, these values of S plus and S minus depend on the choice of stabilization, and they're both less than or equal to the maximum solution, the number of complex solutions. So what are our questions? What we wanted to answer. Given a smooth, finitely determined covariant one map and a stabilization, first question is to obtain a general methods for computing the number of AN singularities for, say, for T positive. The other question, the more ambitious question, is to show that there is a stabilization for which the maximum number is attained, right? Maybe that's not true. If that fails, the aim is to compute the maximum number possible for overall, for all stabilizations. It's okay, the most that you can obtain there. Okay, so these are the questions we wanted to answer. To keep things more simple, I've put a very, very simple-minded example, one that we can even do the computations by hand, directly without any methods. This example is my map germ is going to be this y squared, y to the fourth plus xy. So that the total number of A2, in this case, it's in R2, A2 singularities appearing in any complex stabilization is 2. It's a codimension of this ideal. And I've chosen a particular stabilization that I'm going to use as an example for all the talk, okay? So I'll just added plus or minus t squared y squared to the original germ. So returning to the computability question, we want to obtain this number, S plus of f. And for this, I'll need some more notation. So I'll take the map h of xyt, which gives all the derivatives of my g part of the stabilization, right? This one, this part here, and all the derivatives. So that I want to compute the number of zeros of this map, right? Of this map H. So what the method we developed was the following. We look at the Jacobian determinant of H, okay? Add it at the end to the map H. So you had H was a map from Rn plus 1 to Rn. So I add the Jacobian determinant here and make a new map from Rn plus 1 to Rn plus 1. And I add this, and I make this other map in which I multiply the determinant by t. And there's a general hypothesis to make these things, without it, these things don't make sense, is that the coordinates of H, the derivatives of G, and the Jacobian determinant are 0 when t and xy are 0, okay? So they are in the ring of the maximal ideal of the set of functions. Okay. So the main result, the first result is the following. Under all these conditions, you have a smooth, let me open the rest of the notation here. Here's my G, H, everything written there. So you can keep track of what I'm saying. Under this general hypothesis, and in the conditions that I stated in the beginning, for any stabilization, capital F, the number of positive, T positive AN singularities is the degree of this map phi 1 and plus the degree of this map phi 2. And the number of negative T is the difference of the two degrees, right? So we have a method for computing the number of AN singularities, at least one method. Similar methods to using the degree to compute numbers of things have been used in different papers. Especially, the special one is by Nishimura, Fukuda, and Aoki in 1989, where they counted the number of branches in bifurcation problems. Jim Damon computed in 91, used a similar method to compute branches in symmetric bifurcations. Then Sofia Castro and I used it to compute pitchforks in symmetric bifurcations. And also Cidinha and I use it to compute folds and stabilizations of bifurcation diagrams. Actually, this paper by Cidinha and I was before the one with Sofia Castro, but they came, you know, publication times are not usually the same as mathematical production times. Okay, so, it's a similar method to many things that had been done before. So how do we prove this result? So the result, remind you, is that the number of AN singularities for positive T is the sum of these two degrees, right? So how do you prove that? So starting with this finitely determined corank 1 map and its stabilization, the number of positive AN singularities for positive T is the number of branches in the bifurcation diagram of this map here, right? Because it's the number of solutions of H, X, Y, T is 0 with T positive. So we can interpret it as the number of branches. So we can use the method for counting branches that the Japanese group developed in 1989. And that's what we're going to do. So what is their method for counting branches? So how do they count branches? Given a map H from Rn plus 1 to Rn, so it's a one parameter family of maps from Rn to Rn. And using the Jacobian determinant of H, the number of positive T branches is given by the degree of the map H, T times the Jacobian determinant of H, plus the number of the degree of the map H and the Jacobian without the T. Right, and the number of negative T branches is the difference of the two degrees. So it's an immediate application of this result, gives us the counting of AN singularities, except that we have to check this condition that the codimension of this ideal generated by the coordinates of H and the T times the Jacobian is finite, right? Which we did by a small lemma. It's almost immediate from computing using the conditions for finite determinacy and corank 1, right? So I won't bore you with the details of how to prove that. So this completes the proof of our main theorem. Okay. Once we have that, we have a very nice corollary, which I quite like it. It's a very simple-minded corollary. If you have a stabilization in the conditions that satisfying the conditions of the theorem, the number of AN singularities for T positive has the same parity as the number of AN singularities for T negative. It's immediate from what? Since the number for T positive is the sum of the 2 degrees and the number for T negative is the difference of the 2 degrees, you add the two things, you make a difference. The difference of the positive 1 and the negative 1 is even. It's an even number. So, okay, it's modulo 2. The two numbers are the same. In general, they're not the same, but let's do that simple-minded example that I talked about. So I had this stabilization here, and I computed the topological degree of phi 1. The topological degree of phi 2 is 0, right? That's adding the sign of the determinant of the Jacobian determinant of each one of the phi's in the inverse in the inverse value of regular value of the maps. Add everything. The degree of phi 2 is 0. The degree of phi 1 depends on this choice of alpha, this alpha here, which is plus or minus 1. If you have minus 1, the degree is 2 of phi 1. So the sum of the two is 2, which is the maximum number of maximum possible number of singularities. If alpha is 1, the degree of phi 1 is 0, and that's less than the maximum number of singularities. Okay, so everything works fine in this example, and they're congruent modulo 2, 0, and 2. That's it. Okay. But then computing degrees of maps, I mean, this example is very simple. If you have a more complicated example, it's hard and it's boring. So we looked for other ways to compute the degree that gives us other ways of computing the number of AN singularities. For this, there's a paper in 1977 of Heisenberg and Levine that says that if you have a map from Rk to Rk, and you take the algebra, which is the quotient of the set of functions, the ring of functions, by the ideal generated by the coordinates of phi, then if the dimension of this algebra is finite, the real dimensional, then the degree, the absolute value of the degree is the dimension of this algebra minus twice the dimension of an ideal, which is maximal with respect to the product of two elements of the ideal are 0 in the algebra. Okay. So applying this directly to our result, we can compute the degree, the 2 degrees involved in our theorem as differences in number of dimensions. That's the next result. It takes a sort of lot of writing to state, but it's very simple. I'm saying that S plus of F is the dimension of Q1, which is the algebra for the first phi 1, minus 2, twice the dimension of I1, which is the ideal that is squares to 0 inside of Q1, plus the dimension of Q2 minus twice the dimension of I2, which is the ideal where Q2 is the algebra here, is 0. So that's a nice theorem. Let's look at it in the example. In the example, Q2, you have phi1 and phi2 written here. Here's the Jacobian determinant, T times the Jacobian determinant. Q2 is the quotient of these two things. It can be written as generated by the constant function 1 and the function t over the reals. So the degree of phi2 is the dimension of Q2, which is 2, minus twice the dimension of the ideal, which is 0 here, and t squared is 0 in this algebra, right? And 1 square is not 0, so the ideal that is maximal is generated by t over the reals. Q1 is a bit more complicated. It has dimension 4, and its generators are here. And again, the degree of phi1 is going to depend on alpha. Of course, we knew already that it depended on alpha. So if alpha is 1, this term here is 6y squared minus minus t squared. It is here. So it's a fact, it has two factors, one of which is this thing here. So the ideal that is maximal with respect to being its square being 0 has two generators. So that the degree of phi1 is the dimension of Q1, which is 4, minus twice the dimension of this I, which is 2. So it's 0. So the number of positive t A2 singularities, so cusps, is the number of negative t singularities. Not surprising because t is squared here, and it's 0, right? If alpha is minus 1, then the Jacobian takes this form here. It's a real multiple for this thing. So this cannot split, cannot be factored over the reals. And then the ideal, maximal ideal that is 0 is just generated by one element, this one. And the degree of phi1 is then 2. Okay? So that was a method for computing the degree. There's another method to compute the degree coming from the same paper, which is more complicated to explain and easier to compute. So you have a map from RK to RK, and the Jacobian of this map is an element of the algebra, which is the quotient of the ring of real germs, real functions germs, by the ideal generated by the coordinates of phi. And you have if you take any linear functional from Q to R that is positive on this Jacobian here, you choose one, any arbitrary one that is positive there, and you make the bilinear map from Q to times Q by taking capital L of PQ being little l of the product of P and Q in the algebra. And the theorem says that if the dimension of the algebra is finite, then the degree of phi is the signature of L. That's much easier to compute than trying to find the maximal ideal that is squared to 0, right? So in our case, it's even more complicated to state, but it's easier to compute the result. In our case, we have Q1 and Q2, the respective algebras generated by the two phis. you have this mi, which is, it's called the socle of the algebra. It's the Jacobian determinant with respect to all the variables of phi I, which is an element here of the algebra. You take a linear map that is positive on this M1 and M2, and take the linear map, the bilinear map that is little l computed on the product. And given that, the signature of the capital L is going to be the degree of each one of the phi's. So the number of A and singularities for positive T is the signature of the map L1 plus the signature of the map L2. And for negative T is the difference. Okay, let's look at the example. In the example, we had already the algebras defined, okay? For Q2, for phi 2, the Q2 had dimension 2 over the reals. The socle, the Jacobian determinant of phi 2 is, well, this horrible thing here, which is equivalent over the algebra to the ideal generated, the vector space generated by the equivalence class of T. So you take L2 of T to be 1, L2 of 1, the other generated, to be 0, and then your bilinear map has this matrix here, symmetric matrix, and the signature of that's equivalent to minus y squared minus x squared, plus x squared. The signature of L2 is 0. For Q1, it's more complicated, so I've put it in a different page. So the top part, this top part is the same, but the Q1 is 4-dimensional over the reals. I take the Jacobian determinant, which is up to multiplication by a constant 6y squared minus alpha t squared. And I make little L1 to be 1 in this generator, little L1 to be 0 in the other generators of the algebra. The bilinear map has this matrix. You see the outer part here gives signature 0 because it's like it's equivalent to this matrix. And the inner part, it's diagonal. You have this diagonal block here. So if alpha is negative, both terms in the diagonal are positive, and the signature is 2. If alpha is 1, then there's a positive eigenvalue and a negative eigenvalue, signature is 0, right? And that gives us the computation that we had before. So, okay. So we were happy. We had ways of computing all the things we wanted to compute, 3 different ways of computing the number of AN singularities. We wanted to be more ambitious. We wanted to prove the rest of the project. That's where things got complicated. So we started seeing what we could do after that. One thing was to estimate the dimensions. It's important to have, as you saw, we need the dimensions of the Q1, Q2, I1 and I2 or whatever. So first result was, if there is F is a stabilization of a finitely determined map term F of covariance 1, then the dimension of the Q1 algebra minus the dimension of the Q2 algebra is the algebraic number of singularities. That gives us hope. So we can, so if we manage to, having this result, if we manage to control what's happening in the ideals, I1 and I2, remember, I had some ideals that I had to subtract. If I can control that part, I get the maximum number of singularities. So how do you prove that? The proof is simple. So you write explicitly what Q1 of F is. It's the quotient of this ring of germs by these things, the coordinates of the map H plus the T times the Jacobian of H. And Q2 is the same thing, except that here the Jacobian is not multiplied by T. Then the real dimension of Q1 of F is the dimension of, well, it's the dimension of Q2, here's Q2, plus the dimension of the ring of germs over the ideal generated by the coordinates of H and of T, because both dimensions are finite. So, okay. Now, to finish the thing, the quotient of the ring of germs by H, the coordinates of H and T, is the same thing. You have to remember the coordinates of H are, here they are the derivatives of G with respect to Y, of capital G. But up to if I eliminate all the T terms, I'm quotienting by T here, the derivatives of G, capital G, are the same as the derivatives of little g, right? Because I'm eliminating T. Whoops. This is too heavy for my skirt. Okay, so this quotient here is the same as eliminating the T and making the quotient of E of xy, ring of functions of xy, by the coordinates of little g, the derivatives of little g. And this is exactly the maximum number of singularities. So we had an estimate, we had hopes for that. We couldn't progress much along that, so we went to something else. Let's do a particular case. Weighted homogeneous germs. They're easier to control because you have this system of weights. Since our maps are finitely determined, you might as well assume they're polynomials, right? And since they're polynomials, they could be weighted homogeneous. So we managed to get the following proposition. If you have a polynomial map germ, weighted homogeneous, and suppose the stabilization is also weighted homogeneous, if the variable T, the unfolding variable T, has odd weight, then the number of positive T and singularities and negative T and singularities is the same. Okay, how do you prove that? Basically, you prove that the signature, since the positive T number of F is the sum of these 2 degrees. No, it was not that. It was the degree, the signature of L1 plus the signature of L2. So if the signature of L2 is 0, then the 2 numbers have to be the same, because the one is the sum of the signature of L1 and the signature of L2, and the other one is minus. So they are the same. So it amounts to proving that the signature of L2 is 0. So let's look at the map phi 2, which is on the board there, which is H times H, coordinates of H, the Jacobian determinant of H, right? And since everything is weighted homogeneous, this induces you can put the concept of weighted homogeneous into the algebra Q2, where the L map is defined. So in particular, this Jacobian with respect to the three variables of phi2 has maximum weight, right? It's the socle of the algebra. It has maximum weight. That means that if an element of the ring of germs has weight equal to the maximum, either it is a real multiple of this M2, or else it's zero in the algebra, in the quotient, right? So I'll choose again my linear map to be 1 in the M2 and 0 if in the subspace of polynomials with weight less than m, right? The part in the algebra that's there. So I can divide my algebra Q2 into three subspaces. One is the subspace of equivalent classes that have weight less than half the maximum weight. The other one is the ones that have more than half the maximum weight, and the third one is the middle part, the part that has exactly half the maximum weight. Why? Because if I multiply two things here, the weight is additive with the multiplication. So if I multiply two elements of this Q half, they have maximum weight. And the other ones we're going to see. So I can write my algebra as a direct sum of these three subspaces. Let's look at just these two first, the Q2 less than half of the weight and the Q2 more than half the weight. Okay, if two elements are in this subspace here, then the only way that my bilinear map of P and Q can be non-zero is if the product lies in this subspace, right? That means that the sum of the weight of P and the weight of Q is M, is the maximum. That's the only way to be non-zero, right? Because everything else is zero. Then either P is in Q2 minus, so has less than half the weight, maximum weight, and Q has more than half the maximum weight because their sum is M, or vice versa. Well, one of them is in Q2 minus and the other one is in Q2 plus. So the signature, either their product is zero, or the product is an integer multiple, a real multiple of M2, in which case you're in this situation, and you have a pair that gives you a signature like in that example I had, where I had something like, right, so you in the basis PQ, you get a matrix like this, 0, 1, 1, 0, right? So that has signature 0, contributes 0 to the signature. Or else their product is outside this subspace, the subvector field here, vector space here, and it's outside this subvector space and it's 0. Okay, so signature in that part, in that subspace is 0. So it remains to compute the signature in now you see I'm finishing. Uh, what am I doing? So the contribution to this part, to the signature is 0. It remains to see the contribution, the signature, any non-zero signature is going to come from this middleweight part. So I want to see what is the middleweight part. So I'll compute what is the middleweight. It's the weight of this M2, which is the Jacobian of, where is it? Jacobian of phi 2 over xyt. Now, phi 2 is h, Jacobian of h, with respect to h. So if you write derivative of h2, of phi 2, it's something like derivative xy of h, and then d dt, the Jacobian of h, right, in blocks. So this is, the weight of this is maximum. The weight of this is, the weight of, it's written there. You have the weight of this component plus the weight of this component. That's the weight of M2. And the weight of this component is the weight of the Jacobian of H minus the weight of T. So you have 2 times the Jacobian of H, the weight of the Jacobian of H minus the weight of T. If I'm assuming that the weight of T is odd, this is an odd number. So there is no middleweight part of the algebra. So the signature outside the middleweight part was 0, and the middle part is empty, so the signature is 0. Okay, so that proves, let's see what it proves. It proves that the number of T, positive T, AN singularities is the number of equals to the number of negative T, AN singularities. Okay. For phi 1, we can do a little bit more. As a corollary, saying if I want to compute the signature of L1, then the problem is the middle weight, the maximum weight is going to be even, because I have this T term here. So the signature of L1, the maximum we can say is that it's the same as the signature, for the same reasoning, the signature of L1 restricted to the middleweight part. And we thought, oh, great, we can control it. Well, we couldn't. We were busy doing other things. So we stopped there. That's where we were stuck. So what are the remaining questions? We managed to count everything. The remaining question was to show there is always that stabilization such that say for positive T, the number of ANs, maximum number of AN singularities is attained. This was proved by Cidinha and Joachim Rieger in 2005 for asimple germs, but not for in general. So Cidinha was hoping that with this other type of method, their proof uses totally different methods. She was hoping that with this sort of method, counting by degree, we could prove it in general. The plan was to show it for weighted homogeneous polynomials and then to extend it to the general case. How to extend it to the general case, I have a good idea of how to do it. I never got around to sitting down and seeing how to extend it to the general case because I didn't know I don't know how to show it for weighted homogeneous polynomials, although I always think that I'm on the brink of proving it, and then something goes wrong and it doesn't work. So I was counting with Cidinha for doing this, but now I have to do it without her. Suggestions are quite welcome. That's it. Thank you for your attention. Yeah.
Okay, people, are there some comments or questions or suggestions? So if there is, oops, Miriam, please.
Thank you very much. Thank you, Isabel, for your talk. I have two quick questions. First, because you are an expert on symmetries, so every time I think about the weight homogeneous condition, there is a pattern there. And because you have this proposition that you have the equality of S plus and S minus for the homogeneous
For the
weighted homogeneous case. My question is there a relation, is there a possible relation with between weighted homogeneous and some kind of symmetries that behind this property of balance of exponents that implies, I'm not saying that I expect some symmetries there, but I'm asking about, is there a relation about patterns here and patterns there that you get this equality of the S plus and S minus, which is a kind of degeneracy that we see happening, that's expected in symmetries? I'm not sure if I'm clear enough.
Yeah,
I mean,
you
have a condition.
If there is a symmetry that implies the weighted homogeneous
No,
condition.
what I'm curious is, when you reach the equality that comes from the weighted homogeneous condition,
yeah, you have
this equality,
symmetry
is
in the t variable, right?
yes,
the
indeed,
unfolding
stabilization,
variable.
yes.
In a sense, it is a symmetry that you have there, but I didn't explore that. That sounds like something to be explored.
Okay,
Yeah.
thank you. Another question is that I heard more than once when you came to São Carlos, Cidinha was saying, I have some things to finish with Isabel. And I heard that more than once. My question is this related to what you talked today about?
We started this many years ago, but we were both very busy with other things, right? It's not my main line of research. It was not Cidinha's main line of research. So it was something we tried to do. I remember several times sitting with her in the veranda of her house and with pieces of paper and trying to I have piles and piles of scrap paper written by both of us, discussions, but we never seemed to progress far enough. Yeah. And I always have the feeling that in a sense it's a sort of symmetry in with the weighted homogeneous thing, is that decomposition of the high weights, low weights, and middle weights. It's a sort of symmetry in the algebra somehow, but I never managed to explore that either.
Great, thank you.
Thank you. So thanks, Isabel, for your nice lecture. I enjoyed. My question is maybe a stupid question because I am not at all in this area. Is your H condition for stabilization, is it a strong condition? And do you think to overcome by some way?
No, the condition is just that well, you have to in order to have an AN singularity, you have to have the derivatives to be zero at the.
Yeah, so it's quite a light condition. Yeah, it's not.
It's a very mild condition. Yeah.
Yeah. Okay.
It's just that it has to be explicitly stated. So instead of writing it at length and every time I gave it a name, so as to stop repeating it in every statement of a theorem.
Yeah.
The statements are quite long, and
Yeah,
the ideas are very simple.
Okay, thank you, thank you.
I have some questions. The paper that you told that Cidinha did with Joachim Higger is for map giant from R2 to R2, or the other one with more general paper?
It's a more general
More
paper.
general, okay. And a natural suggestion, but I have no idea how to do it, to extend these results for Newton non-degenerate germs.
I tried to look at Newton diagrams, but
Yes.
I'm not very good with them. So,
Okay. No,
because
just
the Newton
suggestions.
diagrams in Rn are sort of
Yes, maybe in low
n-dimensional
dimensions
things.
it's easier. Okay.
It's in Rn+1, so it's a sort of,
Yeah.
I never got round. Maybe someone who knows more than I about Newton diagrams could help me.
Okay. Okay. Thank you.
If you're the person, we're going to talk. So this was, in a sense, also a cry for help. Anyone who knows about these things, please help me finish the paper. Of course, I could finish with just what we have.
Yeah, of course.
Of course.
Any other questions or suggestions? No? So let's thank you, Isabel, again. Thank you very much.
to speak in this conference. Is quite a honor for me to be here. It's also quite difficult to speak in that moment. So this is a joint paper with Zbigniew Jalonek and José Edson Sampaio. And before I start the mathematical part of my talk, of course, I'd like to say some words about Cidinha, okay? Actually, first time I met Cidinha, she was in the committee of my master defense in Fortaleza. And just after that, I moved to IMPA to start my PhD. And I spent a year there. And the end of the year, I decided to move to São Carlos. And I've contacted Cidinha. And she helped me a lot. She made this dream of, my dream concrete, possible. And then I moved to here to continue my PhD here in 2000, January of 2000. So, and I arrived here, I faced a difficulty because I should to do an exam, a qualifying PhD exam here about the classical singularity theory. That's a subject I had not studied yet before. And Cidinha gave me private lessons about that in her offices in January and February of 2000. And I remember one of the first lessons was about splitting lemma. This is the tools of this talk today. And Cidinha gave me a task to understand the splitting lemma and to explain the motivation, how natural was this result. And I started to study about this lemma. I tried to do my best. Of course, I didn't succeed. And I was upset. And Cidinha calmly told me, no, don't worry, Alexandre. Actually, I know a lot about this lemma because I found this result before to know what was did by Arnold. It was needed to finish my master thesis, and I found by myself. I can explain you, and I understood a lot about this lemma. I learned from Cidinha. So then I was impressed with how she approached mathematics and asked her to be my advisor. And she told me, this was impressive for me. She told me, no, we have a big group of Singularity here, and you have to talk with each one of the group, and you have to decide by yourself which is best for you. Maybe there are other projects, other people here, which could be more interesting for you. And after that, we can come back and talk with me. And I did that. And after that, Cidinha offered me a lot of projects. And in the end, she told me, but if you want, we can study Lipschitz geometry. I know nothing about Lipschitz geometry, but I'm interested to enter in this area. It was impressive for me because of this behavior of Cidinha. Let me, I'm not. Actually, that time she showed me something very special about that. First, her generosity. She helped me a lot to move to here, and she taught me a lot of mathematics in the end of my career. Respect for the students' freedom, and her courage before mathematics. It was quite impressive for me, and I learned a lot of her. She didn't impose a path, she opened doors for me. And the work I will present today is a joint work with Jelonek and Sampaio. But for me, beyond splitting lemma and Lipschitz geometry that I start with Cidinha, this work and this work, I try to show that I learned from Cidinha much more than Lipschitz geometry and splitting lemma. I learned from her, my lovely advisor, the courage to look at difficult problems and the belief that mathematics is better when it is done with generosity. So I choose this picture here because Cidinha was much more than my advisor. She was whom welcomed me to mathematics in São Carlos, of course, opened doors and became part of my personal life and also my mathematical life. It was in Fortaleza, Cidinha, Gaspar, and my family and me. So let me start with mathematics now. The problem. I mentioned the split lemma. I start with the split lemma. Is there a point here? Yeah. So consider a holomorphic function germ, and the corank of the germ is the corank of the Hessian of the germ, okay? The function at the singular point. And this splitting lemma says, this is a generalized Moss lemma. After a change of coordinates, you can write your function in this way. The quadratic part, you are supposing a function is singular, there is no linear part, and terms of higher order here. And the number of variables of the quadratic part is the rank of the iteration, and the number of variables of this residual part is the corank of the function. This is what say the splitting lemma. Actually, it's more common to talk about the corank of the function than the rank of the function, because from the analytic point of view, this is the number of variables you need to address the singularity from the analytic point of view, yeah? Then it's more common to talk about the corank. But if you have the corank, you have the rank. If you have the rank, you have the corank. So there is a book of Arnold, published in 2004, and we have a collection of problems there. And the problem 14, this is the year of the problem, is this one. Arnold asks about the topological invariance of the corank. Suppose you have an ambient homeomorphism that sends the 0 logs of f to 0 logs of g. Is it true that it implies the corank of f is equal to the corank of g? This is the problem proposed by Arnold. There is also a comment in this book about this problem by Vasiliev that Vasiliev told that nothing is known about this problem at that time. So this is a metric version of this is not the original version of the corank problem of Arnold. This is the metric version. What I mean by metric version, I use here by Lipschitz homomorphism instead of just homomorphism. Suppose you have a Lipschitz homomorphism, ambient homomorphism, Cn to Cn, that sends the 0 logs of f to the 0 logs of g. So is it true that it implies the corank of f is equal to the corank of g? So we can ask why by Lipschitz. Yeah? Actually, you will have a lot of topological invariance question about the analytic invariance, which is quite classical and formulated long ago. And in that time, Bifurcation geometry and topology of singularity was not known that they were different. This is quite recent. The people knows the Lipschitz geometry of singularity and topology of singularity actually are different. Then this is why, for me, if you have any topological invariance question, if you ask about the analog metric version, it's natural by itself. So this is the metric version of the Arnold problem. What is new here? Here, I mean, in the paper, in this joint paper with Jalonek and Sampaio, we prove we have a positive answer for this problem, this metric version, for n dimension. Okay? And also in the same paper, we have a positive answer for the original topological question of Arnold in dimension 3. I mean, if you have surface here. But today, I'm talking about just this metric version. And Friday, Edson promised to talk about this, Edson Sampaio, this topological result. So, then the idea today is to give some details about the proof of this theorem here. So we have reduced holomorphic function germs, which are singularity zero. If the zero logs of those germs are by Lipschitz ambient equivalent, then the germ have the same corank. So it's a complete positive answer to the metric Arnold corank problem. So let me emphasize, with no restriction on n. So let me talk about a quite nice consequence of this result. Why corank and multiplicity are related? If you have a germ of hypersurface, multiplicity 2 is equivalent to corank different to the dimension of the ambient. It's the same. Let me come back to the splitting lemma. Multiplicity 2 means that you have quadratic part. Then if you have quadratic part, then the rank is not equal to 0. Then multiplicity 2 is something, some information about the corank. Corank is not maximal. Then, as an easy consequence of our result, is something about the invariance of multiplicities. Let me tell you, topological invariance question, what is well known, is the question by Zariski in 7th early. Zariski asked if the multiplicity is a topological ambient invariant in this sense here. Ambient topological equivalent hypersurface have the same multiplicity. It was a question that time. Nowadays, people consider this a conjecture. And of course, the metric version is here. If you have by Lipschitz equivalent ambient hypersurface germ, is it true that you have the same, the germ have the same multiplicity? This metric version is also an open question in general, okay? Not only the Zariski one. Recently, we have a prominently result by Bobadilla and Pelka about the original Zariski multiplicity question. They give a positive answer just for topological X-singular families with isolated singularities, yeah, with isolated singularities. This is the best we have nowadays about this problem. And as I promised, the consequence of our theorem is multiplicity 2 is ambient by Lipschitz equivalent is ambient by Lipschitz invariant in this sense here. If a hypersurface has dimension 2, then any hypersurface which is ambient by Lipschitz equivalent to the first one has multiplicity 2 as well. Because multiplicity 2 means corank different to n. So the Zariski multiplicity conjecture is pointless in higher codimension, but the Lipschitz question not, because if you are codimension 2 or 3, the link of the germs can be unknotted, and there is no point to consider topological equivalence. Any pair of irreducible singularities which are homomorphic are topologically equivalent. But from the Lipschitz point of view, it's just not true. You have some questions with in higher codimension of this metric version. But for the case of multiplicity 2, we have counterexample with Jelinek and Edison. Multiplicity 2 is not a Lipschitz invariant in higher codimension from Lipschitz point of view. But this is not the point of the talk here. Here we talk about only about one-dimensional singularities, one codimension singularity. So let me start with the machinery to give the details of the proof of the theorem. So the first one is this result by Sampaio, which says, suppose you have two singularities, I mean two analytic germs, which are by Lipschitz homomorphic. Then Sampaio proved that their tangent cone are by Lipschitz homomorphic as well. And also this by Lipschitz homomorphism between this surface carries the singular locus to singular locus. This is the theorem which gives the bridge between Lipschitz geometry and topology of algebraic cones. You see a lot of results about topology of algebraic cones, and we apply to provide some results in Lipschitz geometry using this bridge here, this theorem of Sampaio. So let me say what I mean by cone, definition of cone. Suppose you have a projective variety. Suppose a hypersurface, you have one equation, defined by one equation. So this equation here is reduced and homogeneous. So what I mean by affine cone associated to this guy, the affine cone is the affine variety defined by the same equation here. This is a homogeneous set in Cn+1. This is what I mean by cone with projective base x, or cone with base x. And the link of this cone, which is the intersection of this cone with a sphere, with the sphere of the Euclidean sphere with radius 1. This is denoted by the link of the cone. And associated to this cone, we have a fibration application from that to x, which comes from the restriction of this map here. We have a projection. If line we identify with a point in the projective space, and when you take this restriction of this map to the link, you have a fibration, not necessarily regular fibration with some singular fibers. It depends on the basis, but it's a circle bundle there. Each fiber is S1. So the proposition you use a lot in our result is that Suppose we have two cones like that, with one codimensional cones, with bases x and y, respectively. If the bases are smooth, and the link are homotopy equivalent, then the bases have the same degree. This is more or less easy to see. And when the bases are possibly singular, and the cones are ambient homeomorphic, we are not able to prove the bases have the same degree, but we can prove the bases have the same Euler characteristic. When Zariski proposed the multiplicity topology invariance of the multiplicity, he proposed another thing, is that the invariance of the basis of the tangent cone. If suppose you have two germs which are ambient topological equivalent, is it true that the bases of the cone are homeomorphic? Actually, the answer is no. In general, is no. There is a counterexample by Bobadilla. Okay. But recently, we, in a paper joint with Yalonic and Edson, we proved that if you have homeomorphism between the bases, the projective base, even if the bases are not smooth, they have the same degree. Okay? The degree of the base is the multiplicity of the tangent cone. But in general, homomorphism between the cones are not equivariant with respect to the vibration, and does not induce a homomorphism between the bases. This is the problem in our theory. So, how can you prove the proposition A1? Suppose the bases are smooth and the link are homotopy equivalent. How can you prove they have the same degree? This is the steps. The first step, if the link have the same homotopy type, then they have the same Betti numbers, of course. But how can you relate the Betti numbers of the base? Now you use the spectral sequence of this vibration here. In this case, this is a honest vibration. There's no singular vibration. And its spectral sequence gives this relation. This is the Betti number of the link. This is the Betti number of the bases. This is the dimension, the real dimension of the projective variety. In this dimension, we have this relation. In this dimension, we have this relation. This was in a paper of Peter Orlik, but it's not easy to see this formulation, this statement here. You can see this statement, how it is here in this paper of Koller. Okay, then you use this relation to provide a relation between the Betti numbers of x and y. And also, we have this result, which is well known. If you have a smooth projective variety, the Betti numbers of this variety coincide with the Betti numbers of the projective space, ambient projective space, except in this dimension. They are 0, 1, in odd dimension or even dimension. How it is, how these Betti numbers of this space. But in this dimension, we have something different, which depends on the degree of the variety. Here's this formula. So this statement you can see in this survey by Maxime. So we use this spectral sequence and this formula to show that the Betti numbers of the base in this dimension are equal. But the Betti numbers, using using the formula before, is that plus some constant, and this bet number is that plus the same constant. Then you have this equality here. Then we finish just by this remark here. Then you can prove using elementary calculus. This function is strictly increasing for t greater than or equal to 2. Then this function should be injective. Then the degree of x is equal to the degree of y. This is the proof of proposition 1. The proof of proposition 2, let me remember what's this proposition 2. We have two cones with arbitrary or possibly singular bases. Suppose the cones are ambient homeomorphic, then you have to show the bases have the same Euler characteristic. So let me denote by F the reduced equation of the cone X, and by G the reduced equation of the cone Y. And the degree of F is the degree of X, which is the multiplicity of the cone of X, which is the degree of X. All of those are the same because multiplicity is equal to degree in the homogeneous case. Yeah? So the global mu no fibration, this map, you take a point here and apply to F of this point, is the restriction of F to that. The complement of the cone is equivalent to the local one because the function is homogeneous. Then its geometric monodromy can be right in this way. This is just a rotation because my function is homogeneous. This works for F and G because F and G are homogeneous. Have a rotation with this degree. So then we use a theorem of Le, 73, which says if the zero locus of F and zero locus of G, F and G not necessarily homogeneous, okay? Are ambient homeomorphic, then the induced monodromy action on homology are conjugated. These homologies are linear, and the conjugation is the conjugation of linear maps in the homology are conjugated. In particular, the monodromies have the same left numbers and the same Euler characteristic. Oh, the mu no fiber has the same Euler characteristic. Okay. This is the theorem of Le. We use this theorem in step 3. So then you take power of the monodromy of F and monodromy of G. If the power here is less than the degree of the function, the rotation is not completed. We have a rotation. We have the fiber. We have the fiber here. And we have our rotation. Take a point here, zeta, and this is time zeta. This is the fiber, fiber. If this k, when you take power k, if this k is not an integer multiple of this degree, this point is different to that. It's not a complete rotation here. Actually, this point here is equal to the initial point, if and only if this k is an integer multiple of d. Then my monodromy has no fixed point. Then the Lefschetz number should be equal to 0 by the Lefschetz theorem, fixed point theorem. Yeah. In this power here, which is the degree of the function, this monodromy power, this degree, is just the identity because we have a complete rotation. We start in this point, apply this rotation, and to arrive in the same point. We have the identity. Then the Lefschetz number of this power of the monodromy, O, is the Lefschetz number of the identity, which is Euler characteristic. Since the monodromy of F is conjugated to the monodromy of G, their power are conjugated. Then they have the same Lefschetz number for every K. Then if the Euler characteristic of the fiber, the mu fiber of F and G are different to 0, they are equal. But if they are different to 0, then this degree here of F comes if the first index where the power of the monodromy has different non-zero Lefschetz number. And you see the Lefschetz number here is quite intrinsic. It doesn't depend of the function. Then you have the degree of F equal to the degree of G because of this equality and this remark here. So we are in the case of the Euler characteristic of the fiber, the mu fiber are different to 0. So step 4. Then we take the restriction of this map here, this standard map, to the mu fiber of F or mu fiber of G. Then we prove this is a covering of degree of the function, how it is here. Take the point here in the affine space and take the line associated to this point. Once the mu fiber is not in the cone, this line is not in the basis of the cone. Then this is a covering of this complement of the basis. And the degree of this covering is exactly the degree of the function. Then you have this relation. The Euler characteristic of the mu fiber is the degree of the function times the Euler characteristic of the complement of the basis. Once you have this guy equal to this guy and this number equal to this number, this Euler characteristic of the complement of X is equal to the Euler characteristic of the complement of Y. And you conclude that the Euler characteristic of X is equal to the Euler characteristic of Y. In the case you have 0 Euler characteristic of the mu fiber, you have the same, using this same equality here. This guy is equal to 0, this guy is equal to 0. Then the Euler characteristic of X is equal to the Euler characteristic of the ambient projective space, which is n plus 1. And the same for Y. And this is the proof of our proposition about the topology of the algebraic cones. So now we are ready to approach the proof of the theorem. Let me start with the case where the functions are not maximal corank. The function f and g, they have corank smaller than n. It means the multiplicity of the 0 logs of f and the multiplicity of the 0 logs of g is equal to 2. Then by splitting lemma, you can write f in this way and g in this way after analytic change of coordinates. Then you see the tangent cone of f. The tangent cone of f is the 0 locus of this equation here in So this guy is a quadratic with isolated singularity in CR. Then you have a cylinder of this quadratic. You have the same. You have the same to G. You have the same to G. This is in CS, Cn times R minus Cn minus R. So, in this case, the singular locus of the tangent cone of F here is just this line here. And the singular locus of the tangent cone of G is just this line. So if you suppose they are ambient by Lipschitz homomorphic, zero locus of F and zero locus of G, their tangent cone are by Lipschitz homomorphic. And by Sampaio theorems, the singular locus of the tangent cone of F is by Lipschitz homomorphic the singular locus of the cone of G. Then this guy here is homomorphic to this guy here. Then and lei de triangle. Invariant, yeah. So thank you. So this guy here is homomorphic to this guy here. Then R equal to S. Then the function has the same rank and also the same corank. So then you have to show now just that if you start with a function with multiplicity 2, then the other function should be multiplicity 2 as well. Now, our theorem is reduced to prove that. So let me claim that it's enough to prove this lemma here. This is the tangent cone. I'm supposing that we have multiplicity 2, then the tangent cone of F is this guy, as I described here. And suppose you have a Lipschitz ambient equivalence between the cone of F with the cone of G, which is I denoted by T. And we should prove this T as degree 2. Then I do this restriction here about the rank of F. The case on when the rank of F is equal to 1 or 2 is easy to prove, because the rank of F equal to 1 means the tangent cone is given by this equation. So the reduced tangent cone is smooth. Then the smoothness is a by Lipschitz invariance. Then you have a smooth tangent cone from the other side. And in the case of the tangent cone, the F has corank 2, and the equation of the tangent cone is that. Then this is reducible. We have two cones with relative multiplicity equal to 1. And I've proved this Sampaio. If they are on the other side, the tangent cone should be two planes with multiplicity 1 each one. Have the same. Then the more difficult case to approach is this one, when you suppose the rank is at least 3. But maybe he is smaller than n, because multiplicity is 2. The rank. So let me start. Suppose the lemma is false. Then you have a counterexample, but we choose the counterexample with the minimal degree. Degree D. Once it is a counterexample, the degree is supposed to be greater than 2. But this is the minimum. So S, the singular log of X is this line, then the singular logs of T is not necessarily a subspace, but should be smooth because this Bifurcation is equivalent to a plane. Should be smooth. Then you can choose coordinates, generic coordinates, you put the singular locus as a subspace as well, locally. Then we also choose generic coordinates such that the intersection of the coin with the bottom is isolated singularity. So the singularity actually are here, and this intersection is isolated singularity here. But T is not, I'm not supposing T is splitted. Not yet. Okay. So we have a remark here. If you consider translation along this singular locus, what I mean by translation, we have a vector in this subspace, and you take the translation of the ambient space in this direction. Since the singular locus is linear, is linear, these translations preserve S and the singular locus of S. So, then the germ of each point here, the germ of S, we have S here. The germ of S here is by Lipschitz is equivalent to the germ of S here by translation. It's actually translation Lipschitz equivalent. So it happens the same in the other side. But this equivalence is not by translation. We have to conjugate with the Lipschitz map, ambient Lipschitz map, with conjugate X, S, and T. This one. So this guy is not splitted. You can have something different here. It's a cone, but it's not a cylinder. And this guy here is by Lipschitz equivalent to this guy here. In particular, what we have that is the degree of the tangent cone of T in any point of here should be equal to 2 or D. Because this guy is by Lipschitz equivalent to this guy is by Lipschitz equivalent to this guy, this is S. Then the tangent cone of T in this point is by Lipschitz equivalent to S. And then by minimality, it cannot be different from S and D. Yeah. DO2, exactly. So you have two cases to analyze. The case one, this degree happens is equal to D in a dense subset of the singular locus of T. We have a dense subset here, where this degree is equal to D. In the other case, we have a generic, for generic Z in the singular locus of T, this multiplicity is equal to 2. Let me consider the first one, the branch A. Suppose we have D in a dense subset of the singular set. So using that the multiplicity is upper semi-continuous, we prove the multiplicity is equal to D in each point of the singular set. Each point of here, in every point here, the degree of the tangent cone, this is T, is equal to D. And we state that for the projective closure of the singular set. We also have the tangent cone of the degree of the tangent cone as degree d when we are in the at infinity of the singular set, as I mentioned here. So if you take a point at infinity of the singular set of d here, point at infinity, point here, take a line, it passes to this guy, take a point there at infinity, we define this line. The multiplicity of the tangent cone in that point is equal to d, as I mentioned. And you take a point of t take a point of t here, sorry. Take a point t here. And take a point in the singular, at infinity of the singular locus here. And take this line. Okay? The degree of the tangent space here is equal to d, because, let me show this point equal to alpha. Because this point is the singular locus. And the degree of this point here is at least 1. So using Bézout's theorem, the number of points in this intersection is at least d plus 1, which is greater than the degree of the cone. Then the line is inside of the whole line is included in the cone. So this proves the cone splits. Actually, this cone is a cylinder like that. In this part, guy is isolated singularity. Then S is singular, isolated singularity in CR times Cn minus R, here, this picture. And T is the same. You have a singular, isolated singularity in CR, the same here? No, CS, yeah. CR, CS, I don't know. And you have a cylinder here. Then the complement of the singular set of S, let me take another picture. We have a cylinder, and the singular set is that, and we remove the singular set. We remove the singular set. Then the homotopy type of this guy, when you remove that, is just that. It is the link of the cone. Then we have smooth bases, the cone with the smooth base, because they are isolated singularity, and their link has the same homotopy type. Then by proposition A1, the degree are the same. And the degree of S is equal to 2, and the degree of T is equal to D. This is a contradiction. And in the other case, this is a delicate part of the paper. This is not easy. I will skip the proof of that. We prove our tangent cone splits, but the basis here is not isolated singularity. It's a one-dimensional singularity. You can write, you have equation, homogeneous equation for the cone, which depends of R variables plus only one variable, and the singularity lies in this direction here. And you can write your cone in this way. So this is a delicate part of our paper. once the Euler characteristic of the bases of S and T have the same Euler, sorry, the base of S and the base of T has the same Euler characteristics, we can prove that if you cancel here some C's, here, if you cancel, and you cancel the same here for S, they have the same Euler characteristic because you cancel one in the computation of the Euler characteristic. Then you prove that this guy here in CR plus 1 have the bases of this cone have the same Euler characteristic of the base of this cone. This is a cone with singularity only in this line here, 0, 0, 0, x1, 0, 0, 0, x1. Here the same. So the basis is here is a quadratic hypersurface with singularity only in one point, the 0, 0, 0, 1. And you have the same here, 0, 0, 0, 1. And for this kind of hypersurface with isolated singularity, we have a formula to the Euler characteristic. We can find this formula in this paper of Parushinsky, which depends on the degree here, the degree, but we have some residual terms here, which are depending on the Milnor number of the singularities. They are isolated, they are finite, and you compute the Milnor number. Since this guy is a Morse singularity, the Milnor number in this point here in the projective space 0, 0, 0, 1 is equal to 1. You have the same here. Because of the hypothesis, you have generically we have multiplicity 2. By this formula here, of course. This formula. We have quadratic singularities near when you developed your function in this singularity here, x equal to 1 and other ones equal to 0. Then using this formula to this guy and this guy, you have this equality here. This is the formula for T, and this is the formula to S. The degree of S is equal to 2, the degree of T is equal to D. Then you finish that using this function, which is increasing, strictly increasing for x greater than or equal to 2. Then D should be equal to 2. We arrive in another contradiction. So this is the proof.
Hello. There are any questions or comments?
So first of all, thank you very much for this nice talk, Alexandre. My question is about the generalization of this problem for maps. So you present a proof for functions, but I think that the same problem can be considered in a pair of maps or in a family, topological trivial family of map terms. What you can say about the constant of the Corank in a topological trivial family of maps? The same technique can be applied.
The Corank, what is the definition of Corank in the case of map?
In the case of map, you can calculate the Jacobian matrix, and you can look for the rank of the Jacobian matrix, and you consider the difference of the maximum of the dimensions
The
of
Jacobian,
sources and the
not the
target.
Hessian, the Jacobian.
The Jacobian.
The Jacobian, I
sorry,
see.
The Jacobian.
And if you consider the by-Lipschitz equivalence of maps,
By Lipschitz.
this is a by-Lipschitz invariant.
Okay.
The maps, because if you consider the bi-Lipschitz invariance of the functions, the right equivalence of functions, it's easy to show that.
It's not hard. Okay.
Yeah. If you consider the bi-Lipschitz equivalence of maps, this is easy. But if you consider the bi-Lipschitz equivalence of the zeros, locals, or the double points, I don't know how to approach.
Okay.
Maybe.
Okay. Okay. Thank you very much.
Any other questions or comments here?
Hello, Alexander. Thank you for the talk. That's a really incredible theorem. And I became curious because the proof is very geometric, and you take the smart move of taking the line at infinity and use Bezier theorem. I really like that. But I'm curious because it seems that you developed a lot of general theorems, and why does this fail for multiplicity bigger than 2? I'm trying to visualize that. Where it fails for multiplicity bigger than 2?
We start with the split lemma.
The split
lemma is very
it's
important
for
here.
quadratic.
We don't have a standard form to the tangent cone in higher multiplicity. At least maybe.
Generalization of Parushinsky theorem. Yes, in fact, we have not a good method how to compute Euler characteristic if we have singularities which are not isolated. This is the main obstacle to generalize this to general case. This is a risky multiplicity problem. Yes, and I believe that maybe in further in our common project. Yes,
actually, we have a paper which is it's not considered to publication when the first part of the function is von Briscoe.
Yes. But anyway, we need some suitable formula for the Euler characteristic of singular hypersurface. It is done in some cases by Parushinsky, Pragach, but this is not enough. Yes, this formula is not so geometric to be applied here. Yes, there is only main obstacle, this formula for Euler characteristic, and if we have this, we can finish. Yes, and we can obtain the risky multiplicity for by Lipschitz mappings.
Wow.
Yes. It is the effort of 5 years of our cooperation. Yes, of course. I learned Lipschitz geometry from the school of Fortaleza, yes, and also here, yes.
Are there any more questions or comments? No, so we thank you again, the speaker.
Thank you, Marcelo.